recording. Have you had that before? You just
Never
need
had
to
that
say, okay.
before.
You just got to say yes. I'm okay with it.
Yeah.
Um, but it's great to have you come and chat, Rob. And I
Thank
will
you for
let you
having me.
do a little introduction of your background so that people who listen to this later on might have an insight of where you're coming from. Um, I met Rob at a Freedom Festival a few weeks ago, and um, he listened to my presentation on electromagnetic full flat universe theory, or some of it anyway, that I was able to unpack in an hour. And then, and he very kindly was very generous in saying, it was interesting. But of course, he comes from, well, he can talk about his own background, but he comes from a very scientific, and well-educated background. So it'd be interesting to see, hear the differences. I'm not really trying to change Tim's mind. I'm sorry, Rob's mind. I'm not trying to change Rob's mind at all. It's really just sharing information and ideas, I think, and trying to build on what we know, and see how it stacks up in the quantum kind of conversation, and perhaps even the nature of our reality.
Yeah,
So why
so
don't you just tell us a little bit
I'll do
about
a brief introduction. So I'm Rob. I've just finished my master's studying physics and maths at Durham University, kind of specializing in particle theory and theoretical physics. So I saw David's talk, and obviously I was interested in kind of the electromagnetic side of it because we spend a good deal of kind of university covering this sort of thing. And yeah, I was kind of interested to learn more, and hopefully we can kind of teach each
Hmm.
other something.
Yeah. Well, thank you. That's really. Did you say you went to Durham?
Yeah.
That's a For people who don't know, that's a well-respected university. It's a good school,
Mm.
and you have to be a pretty good student to get in the first place. So you obviously did quite well at the physics.
Yeah.
Um, so just to kind of hit a few of the just to kind of kick off to say that a lot of science today is based in theoretical concepts
Mm.
that are accepted by the majority, or the consensus. Um, and in physics, I don't know if it was you who said this to me, but I've spoken to a few scientists over the times. I do the street activism, and a few have said, we don't necessarily test the things in a physical way. We can test them sort of mathematically, and hypothesize about how things might work. So I just wanted to kick that off, I suppose, and say that because when we're in a world of theoretical understanding, then it's it we can get lost in our certainty that this theory
Mm.
has to be all that it is. And the Piltdown man was an example of where we kind of come up with a theory and people stuck with it for a while until they found out it was a fraud. And I'm not suggesting that people are intentionally in any kind of way being
Mm.
fraudulent, but once you're kind of schooled in a particular theory, then it's harder and harder to look at other alternative models, and we see this even in mainstream physics. Where people, you probably understand this better than me, but people have taken the mass attracting mass Newtonian gravity and then superseded it with Einsteinian, but some people
Mm.
want to stick with the Newtonian, and it has to be the mass attracting mass thing. And then in the quantum side, guys are looking, if I understand my study of the quantum side, the guys are looking back at both of those theories and saying they've got holes in them, and
Mm.
they don't they can't be the complete picture. There's things that we understand and see now that mean that all of that
Mhm.
idea doesn't sit with what we're able to observe.
Mhm.
And that's great, but it's also it's like in medicine. The old doctors will struggle to let go of the stuff that they were taught in their day, and then the younger doctors will come through and say, no, well, we don't need that anymore. What we're going to do is going to build from this point forward without that. But
Mm.
there's plenty of doctors who say, no, no, you have to have that. um
Yes.
yeah.
I
Carry on.
mean, I think the like all of the physics has to be kind of rooted in kind of experimental observation. And I think
Mm,
there's a bit of um, physics is quite a tricky one because some people can kind of like the maths kind of tells its own story.
mm,
And like for instance, there's been many times in the history of physics where someone has written out an equation and it turns out that that equation has some sort of kind of crazy outcome, something that like people can't would say that, oh, that's nowhere near physical, and then it
mm.
turns out to be true. So like the good example is the Dirac equation, where
I
Paul
heard of
Dirac
it.
uh,
Yeah.
tried to link electrodynamics and quantum theory
Hmm.
together. It was kind of the first attempt of kind of unifying these two fields, and he wrote down this equation and um, he got solutions with negative energy. And this kind of worried everyone because obviously, like, normally in physics, when you get a solution that has negative energy, you just kind of throw it out. But he was of such a mind to say, no, I actually think there is these things that have negative energy.
Hmm.
And if we now know that these things are antimatter, so antiparticles, so he predicted the anti-electron through this
Okay.
equation. So I think a lot of physicists they have this conviction that if the math is beautiful and if the math really works,
Yeah.
then the reality will follow. Unfortunately, now that's kind of like the string theorists, so like the dominant theory,
Hmm.
um, theoretical physics that's tried to unify Einstein's relativity and quantum mechanics.
Okay.
Um, they've kind of been, I want to say, led off astray with all the digging deeply into like this amazing world of pure maths, but
Hmm.
in the 50 years that they've studied it, they haven't been able to make a prediction. They haven't been able
Right.
to falsify their theories. So they're kind of they're doing a lot of maths work. They're making very important contributions in kind of pure mathematics, but
Hmm.
it's not necessarily physics as we'd known previously. So yeah, I think it's kind of in the quest to kind of unify these two things. I think physics has kind of recently been brought astray
Hmm.
by kind of chasing these ideals, but not testing them or not making any predictions out of them.
Right. And the quote from Nikola Tesla, which I may have mentioned the other day, you probably heard it yourself, about how modern scientists are getting so caught up in the mathematics, they're starting to construct a reality that bears no resemblance to the
Mm,
physical world. And and well, he gets something. I'm probably butchering that a bit, but they run off in equation after equation, and you saying what you were saying about the string theorists made me think about that. I mean, I don't have a sort of a dog in the race when it comes to which of those theories works, or how it can be tied back in to make the relativistic view of the world work, because I'm
mhm,
obviously trying to develop the idea that actually it's all like it's all electromagnetic,
mm,
toruses, energy in constant flux in flow, rather than electrons going around a nucleus, and that
mm,
kind of that kind of idea, which is really, I think, what science is still wrestling with, is trying to
mm.
make all of that stick, as it were, right?
It's kind of funny because the higher up in physics you get, the more bizarre reality becomes. Like
Mm,
there's some things that like kind of we go through, and it's just like it's kind of mind bending things, and it's especially in the quantum side of things. It's so far away from our experience, like our everyday experience. Like, you know, things can't be two places at once. And, you know, things can't teleport, things can't do all of these different things. And yet, when we make observations at these small scales,
yeah,
it's kind of our leading theory suggests that this is how the universe works at this small scale.
yeah. Is that, are we saying, if I can simplify it into layman type terms, are we saying that the observer is affecting reality?
Yes, there's again, this is where I would say both theories, so quantum mechanics and general relativity, have holes in them, these big gaps of knowledge. One of them being in quantum theory is the observer kind of problem.
Yeah,
Um, so the way we kind of describe these things is the the wave function is how we describe particles, and when we observe the wave function, it collapses into a definite state, which is how we can get from these weird wave-like probabilistic things to discrete
mm,
concrete particles that we can observe.
mm,
And there's some amount of that that's based in kind of the observer can be anything, but the fact that you look at the system fundamentally changes what the system is doing. So in some
yeah,
it's so crazy. Like in
yeah,
some way that like the mere act of measuring, the mere act of looking at something changes it
yeah,
fundamentally at
yeah.
a fundamental level, and it's just kind of it's that thing of kind of how much of that observer, how much of the wave function collapse can be put on the observer, and it's still an open question.
Mhm.
Like it's still unknown quite how that mechanism works, and that's hopefully why combining the gravity and relativity side will enlighten that. But at this kind of point in theoretical physics, we don't really know quite how that happens.
Okay. Can I ask you like a practical, real world example of the world that I consider, and I think, how is that explained in the mainstream? And the example is this, that you take 100 kilograms of dry timber and throw it on a fire. In the morning, all you've got left is hundreds of grams worth of ash. And
Mhm.
all that left in between you lighting the fire and this morning is heat and light.
Yes.
So we've lost 99% of the weight or
Mhm.
mass. And we all we left, so all that left was heat and light. No physical weight
Mm.
was seen departing, just heat and light. So what would be the kind of quantum physics or the mainstream science explanation for?
So this can kind of you can the well Einstein's famous E equals mc squared
Mm,
kind of comes into this. So kind of there's an exchange rate that you can make between energy and mass. So you don't have to have mass conserved in interaction. So especially when we're talking about kind of chemical bonds or subatomic particles,
mm,
it's quite fluid, changing mass to energy in the form
energy,
of light and heat.
combustion, or yeah,
Um, so I think the conventional view of explaining this stuff would be that kind of the chemical energy that's stored um, is kind of well, first off, the combustion releases gases, which
yeah,
also take away some of the some of the mass,
yeah,
but then there will be some amount of mass that is lost, changed into kind of photons of light.
yeah. Well, that's why, I mean, for me, like, because with the dark matter question, that the universe is all this weight or mass, I
Mm.
should say, and yet it's undefined, or it makes up so much of.
Yeah, that's like I would say probably one of the catastrophic failures of kind of astronomy, um, is that we don't really know what 98% of the universe is made out of. Um, and it's kind of everyone, all the scientists kind of go about their day and all publishing loads of research papers, and there's still
Mm,
this kind of big thing of like, what is this? What's the 98% of the universe? Um, so kind of how they got to that number is by, I'm not an astronomer, so this is kind of a bit out of my depth, but
Yeah.
from my understanding is they look at spiral galaxies and the speed of rotation
Mhm.
of these spiral galaxies, and they have a way of modeling, and they have the theory behind how fast these things should spin depending on how much stuff there is in the galaxy. And what we find is that when we do the calculations, there's a lot less stuff that's causing these things to spin. So we kind of put that up into dark matter, dark energy, things that we're not quite sure of the real properties of, but
Yeah.
there have been some theories kind of tentatively explaining what's
Right.
going on.
Right. Well, because it's an interesting percentage because, going back to my 100 kilograms of wood,
Mm,
there is only about 2% of material left when you sort of put it on a
mm,
scale at the end of the day. And so for me, as someone who thinks that this is an electromagnetic um, uh, uh, sort of theater or expression that we are interpreting as a tree,
mm,
that actually what I'm looking at is an awful lot of dark matter and just the sort of it being held together in a certain density to give it a certain mass.
mm,
um, and it's that density that obviously needs to be broken back down again in order to create that sort of rupture, that heat, that light,
mm,
and so on. So it fascinates me that everything is micro and macro in my conception.
mm,
So if what I can see in the microcosm, in the form of the tree and so on, that wow, it seems to be all of this mass. It's 100 kilograms of mass, and now it's actually, when I analyze it, it turns out to have just been a lot of light,
mm,
mostly just light.
mm,
And in the electromagnetic, it's the breaking of the bonds, perhaps, of the electricity and the magnetism is ripping them back apart, which is creating that heat.
mm. Are
Um,
you are you aware of the Casimir effect at all?
I've heard of it, but I'd need schooling on it.
So this is kind of another weird, bizarre quantum phenomena that kind of links to the interchange of
Mm,
energy and matter. So in a vacuum, or basically, as long as there's sufficient energy that's available,
yeah.
you can spontaneously create um, like a matter antimatter pair that
Okay.
quickly destroy each other.
Okay.
Which is, but the thing is, we can't really observe these type of things, but our calculations say that they should be there, and it's kind of the thing that kind of they kind of appear and disappear so quickly that it
Yeah.
kind of, they can almost borrow energy, like they can borrow ambient energy from the space to do this process.
Okay. Have
So it,
you? Sorry,
go
carry
on.
on. Finish.
No, go ahead. Go ahead.
Well, have you on that vein? Have you, as part of your uh, phenomenal education? I'm not trying to be at all facetious when I say that, but you've had a good education. Yeah, have they included any of the work of Nikola Tesla and what he was saying about the universe? Do you study that much?
We do a little bit of Tesla when we study electromagnetism, but to be honest, it's not a big part of the
Okay.
curriculum.
Okay, because you may or may not have heard this said of him. Now, obviously, what I know of Nikola Tesla is only what I can find on
Mm.
on the internet. Is it all true? Is it disinfo? I don't know. So, and I'm not a physicist. However, it seems he was able to extract free energy. They might call it implosion energy, but some kind of latent potential that is in the air, the ether,
Mm.
I call it, and and that there is, as he said, apparently in my hand enough power, energy to power a city for years, just in
Mm.
the ether in my hand.
Mm.
Does that tie with what you were just saying about negative energy or free energy?
Yeah, so the the conversion rate between energy and mass is this equals mc squared, the speed of light
Mm,
squared, which is an enormous
yeah,
quantity. Like,
yeah,
it's a kind of, you can't even comprehend how how big these numbers get. So like a
yeah,
tiny, tiny bit of matter,
yeah,
if you could release all of it, has an enormous amount of energy. So he's probably not wrong in saying that, like, kind of, like, in the palm of his hand, he could power an entire
yeah,
city if only there was a way of kind of converting all of this energy,
yeah.
all of this matter into kind of free usable energy. So it's kind of the thing of a lot of thermodynamics and a lot of the early studies of kind of steam engines and like theoretical underpinnings of like heat
Hmm.
was kind of how do we get energy in like useless form into energy that we can harness.
Yeah.
So obviously, like coal is a great example of kind of energy that we can easily harness. Um, and it's kind of, I think it's just very difficult. It's very like, even though there's so much energy like
Mm,
all around us, it's
mm.
incredibly difficult to get that into a usable state where we can kind of focus it to do mechanical work or electrical work.
Well, so just, I mean, just a thought on that is that, if our world works on combustion explosion type
Mm,
energy, and I think that the thinking of that time, or maybe those kinds of scientists, was that there is an implosive force that is far more efficient, far cleaner, and will deliver a lot more than this explosion thing. And I think that
mm,
the star in a jar experiment using the sonoluminescence, where they fire that frequency into the liquid,
mm,
and they create that cavitation, and then
mm.
their forces are so great that they get a star to emerge in the lab.
I'm
Um,
not quite sure. I'm not quite aware of that exact experiment, but I can look into it. I know there's a lot of stuff taught about optical cavities, but I kind of never
yeah.
really got a chance to look
Oh,
at that.
okay. Yeah, you should look at that. I think as and maybe if we have another conversation, we can show it. But the star in the
Yeah,
jar, it's not at all conspiratorial. An accepted
yeah, yeah.
sonoluminescence is an accepted phenomena, and people have been experimenting with that. And of course, I mentioned, I think, to you the primer field experiments, which was part of my journey done by David Lapointe and others since 2008,
Mm,
which was an important part of my sort of stepping stone into considering electromagnetics as the key building block, if you like,
mm,
of our entire structure here, the universe, as we call it.
mm,
And what you were saying just now about the scientists talking about, I forget the name, but talking about creating that um, negative energy, or what did you call it? Zero
matter and antimatter pair.
antimatter. So so that works for me in the electromagnetic conversation as well. Because if we're looking at the torus system that is both running up and out itself and then back into itself like the reciprocating
Mm,
hyperboloid, then I think that you have a zero and a 1 point in that, you have an entry and an exit,
mm,
and that this is what's driving the whole thing, is that it's kind of going through a black hole cycle where it's
mm,
flipping around, going to zero and then getting back to one again, which is what light is always looking to do. But it needs that retardation. It needs to be stopped
mm,
at and it's in that stopping that I think so much force or energy must be
mm,
created in that moment. And if I showed that on the macrocosmic scale, then it might look like the magmatic pools that we have beneath our feet, in the area below the crust or the mantle or whatever. There is this hot layer, and that would be, in my view, where the one becomes zero, and then it enters through that kind of black hole, and once it leaves the black hole, then it's expressing itself to get back to light speed, and then
mm,
it's doing this. And
mm,
so you on both sides of that, it's almost like the yin and yang, but on both sides of that you got -1 and +1. You got, or
mm,
zero, yeah, -1 to into zero, and then back to a one again.
Mm. There's a big part of kind of theoretical physics is like kind of these conservation things, as kind of you were kind of alluded to, of kind of the universe being in kind of constant states of flux. It's kind of, it's very similar in the fact that like there's a lot of things in the universe that they have the freedom to do whatever they want as long as they kind of conform to these kind of conservations. So like electric charge is a thing, is an example of kind of, yeah, you can have positive and negative, say coming into an interaction, but that kind of the sum of those two must always be the same coming out of it.
Mm,
And and like energy and mass equivalence, like you can't create energy. You're only transforming it between different
yeah,
states, and it's kind of everything's kind of in a flux of these different kind of forms, but are always underlying
yeah,
kind of these conservations.
yeah.
Um, and just a very cool thing about these conservations is Emmy Noether. She came up with this Noether's theorem, which I would say basically you use every single day, kind of professional theoretical physicist, and it links these conserved quantities to symmetries in
Hmm.
nature. So that there's like kind of there's a fundamental linking between the symmetries we see in nature and these conserved quantities that we measure. So it's all like crazy linked together in a like a really beautiful way.
It is, it is seems to be linked in a beautiful way, and you see these sacred geometric patterns. Well, geometric patterns, if you want to be in the sacred world. But I think that there were these beautiful patterns and spirals and Fibonacci and all these things
Mm,
that we see in nature that are for me so wondrous now as a former atheist,
mm,
and an evolutionist, is that they are wondrous. That these are magnificent mathematical, sort of constructs that seem
mm,
to inform and control the actions of pretty much everything
mm,
from the microscopic to the macro, including the movements of the luminaries in the sky. They on a flat Earth or a stationary Earth cosmology. When we look at these things, and I think it applies on the heliocentric model too. But when you look at the orbits of these wandering stars, they draw these beautiful flower of life patterns, and so that's happening at the macrocosm as well,
mm,
and down to the smallest cell. Which so when I think in terms of the electromagnetic torus, I say to people, I think that we may well be an electromagnetic torus ourselves, but within us we have smaller toroidal
mm,
systems that are in operation, right down to the cellular, the very smallest level. That everything is at the cellular, which is my preferred, as I said to you earlier today. I think my preferred conception is that when we look at quantum physicists talking about the flow of where they will be able to not with 97% accuracy to say that the electron will be found in this
mm,
pattern, in this path, somewhere in here, in this nest. I say
mm,
that's because it is everything is free, everything is vibrating all of the time. Maybe you're only able to isolate a particular moment and catch something in a moment, but everything is sort of constantly moving. The idea that vast space, obviously at the quantum level, but vast space exists between the electron and the proton and neutron and so on, is a way that we try and understand it in our world. But actually, everything is like a foam, or a sponge. Everything is just connected together, and obviously a sponge has got lots of
mm,
gaps in it, but everything is like in a sort of soup, and it's this constant movement within that soup,
mm.
at the small and at the macro level.
Yeah, there's a lot of like kind of connectedness. Are you um, aware of kind of um, like Feynman's interpretation of QED at all?
I've
These.
heard it. You know what? I studied this quantum stuff in 2019, in between various other challenges that I had going
Mm,
on in my life, and so I did a lot of listening, but I didn't take a lot of notes. So
It,
I
it's
haven't
one of,
retained it very well, but I have heard it.
it's one of kind of the most bizarre things that I learn of kind of the way that you consider, say, the path. Say if you have 2 points and you're shining a laser beam.
Hmm.
Say the one way of kind of formulating how this works is to say that the light travels every single possible path
Hmm.
between 2 points. It like however weird and wacky the travel is, you consider it, and then essentially by adding up all of these things, all of these different possible, infinitely many possible paths that
Yeah.
light can take, you regain what we observe. And like kind of on the macro scale that happens, but when it this kind of thing breaks down is when we get smaller and smaller scales.
Hmm.
These infinite paths don't just produce one observable thing. We now see many different kind of observable paths, which is why we get kind of the double slit experiment interference patterns. So yeah, it's kind of everything's weirdly connected in it, and
Yeah.
in this formulation, kind of everything's taking all these. It's like almost searching out all the possible space that it
Yeah.
can, taking all of these different possible parts, and yet when we
Yeah.
look, it kind of combines into one.
One beam that
Yeah.
comes to the eye. Yeah, I mean, it's, so I'll just throw this at you, Rob, that
Mhm.
my idea, it's not necessarily, it was certainly wouldn't be my idea on my own, but my conception at the moment is that we have this medium that we're existing. It's called the ether. That's what I like to call it, like they used to call it, the ether. And this ether is almost like it's almost like all of it has total, it has potentiality, every bit of it, and we can think in terms of cells or little honeycomb or whatever, but every little bit of it has the equivalent potentiality for transporting data, light, sound, you know,
Mhm.
etc. So when you point a torchlight at the at, in a direction towards your friend, then all of the all of the ether material that is able to receive or is within the range of the reception of that beam is all going to be ignited or initiated to carry a certain amount of luminosity, depending on how close it is to the
Mhm.
original source. And so that's how I think that and so in that case, then the light can sort of fill the space in like in many zigzag kind of
Mm.
ways because it's just moving its way through the sort of the honeycomb like
Mm.
and but it can do that almost like a you know like a bolt of lightning,
Mm.
but all we see is a single
Yeah.
clean.
Yeah. So that's exactly that's very similar to kind of Feynman's insights and kind of how electromagnetism, like kind of interpretation of it, is how he thought of it. It's very similar. I think um, to get to your point on kind of the ether, I'm not sure many modern physicists would call it the ether, but kind of that the idea that you're putting across of kind of this like field of potentiality at
Hmm.
which things happen in. I think the modern interpretation of this is kind of encapsulated in Einstein's general relativity, where kind of we have fields
Hmm.
and quantum field theory. So everything, all of modern physics is based on the idea of kind of fields permeating all of space and all of time,
Hmm.
and we kind of do physics based on the kind of the interactions between these fields and the potentialities within these fields. So I think again we wouldn't use the ethos per se, but the idea of a permeating field
Yeah.
still persists. It still successfully explains
Okay.
phenomena
So
in
how
these things.
how how is the permeating field? Let's just say so, just to keep it within the confines of the world that we can test ourselves. So let's just say in our atmosphere,
Mhm.
is that one field, or are there multiple fields within that?
So, to my knowledge, there's multiple, but I could be wrong. There could be one unifying one that I'm not aware of. But in the current understanding of it, of quantum field theory, at least to my knowledge, we have fields for every fundamental particle that we observe. Um, so each has their own field, and each can only interact with a certain amount of others. So off the top of my head, there's 12 or
Okay.
13 different kind of overlaying
Mm,
fields, um, with which we kind of use to explain particle interactions.
okay.
Um,
I won't try and understand that anymore at this point in time, but that is useful. Thank you. So from my conspiratorial perspective of
mhm,
science, I learned along my reviewing and restudying science that what's his name, Tesla, was pretty certain that there was an ether.
mm,
Um, and you take it's an interesting way they spell it with the
yes.
Aether.
Yeah.
That's the way of spelling it. And the word breathe has got all of those
Mm.
letters in except with the extra B. So I've found other words that the ether like that. If you add a C, I think you can make create. Um,
Mm.
something there was a bunch of words I looked at with regards to that. And anyway, on from the conspiratorial perspective,
Mm.
the story goes that interferometer results were picking up what I understood to be an ether drift
Mm.
of 15 degrees an hour or something, but it was measured at 3 or 4 miles an hour from the Michelson and Morley experiments in the
Yeah.
1800s. And that the ether was changed out of scientific lexicon because it sort of interfered with the Einsteinian progress with
Yeah. The special
relativity.
relativity. Yeah.
Yeah. So that's how I understand that. So not wanting to necessarily get into like whether that was right or wrong, or is that's
Mm.
true or not. What I do notice in the world that we live in today is that we have something called the Ethernet, and we
Yes.
use the
Yeah.
Ethernet to transmit vast packets of information data
Mm.
from one transmitter to another receiver,
Mm.
sometimes very far distances away, and if you believe in satellites, and sometimes in tens of thousands or thousands of kilometers away. Be that as it may, what I'm fascinated by is that how is the entire box set of 24 or whatever it is that you're downloading through
Mm.
your streaming service, how is all of that intelligence coming to my device? I think the mainstream is sending a wave,
Mhm.
propagating some kind of wave, and all I've got in my mind is the radio waves that are coming, or
Mhm.
other things that are coming in sort of waves and so on. But in the way that the light, torchlight, informs the field, the ether, such as to turn on a certain amount of brightness, because every torch is different, and the distance and all that will
Mm.
make a difference. So it's going to give that bit of ether in front of me a certain bit of information that'll cause it to illuminate
Mm.
until I switch off that thing. Well, I think the same thing is happening with possibly with the data that I'm sending, is that it's illuminating the ether with the data that I'm package that I'm sending it, and that sort of package is being passed as far as it can be passed. In the case of a 2 or 3 mile away receiver, it can be passed directed to that and received
Mm.
in that, and then taken underground through fiber wires to America or wherever it's going.
Mhm.
Because as we know from the data industry, 99% of all data traffic is on the cables.
Mm.
So how do you feel about that? I mean, how does that challenge the understand that the way that you're taught to see that?
So I think it's again very similar. This kind of ether field has kind of been kind of replaced by these like three other well, two other fields would be like the electron and the photon field, which are kind of the main sources of how we transmit these information, and very much the same as kind of like the information that we send via light or via kind of fiber optic are just kind of fluctuations in this field, and they carry almost like waves through this field or packets through this field. Um, and then obviously when it gets to your kind of Wi-Fi transmitter or your Ethernet cable, it kind of then sends it on to wherever it needs to be. But again, it's very similar to kind of the fundamental side of what we would expect kind
Mm.
of in a modern physics perspective.
Okay, well, so just just so I can sort of express, even though obviously I'm coming in from a sort of non-scientific background, just for me, I have this beautiful idea that the ether around me has the ability to carry all of the information in that box set of 24. It has all the ability to carry that, just like Tesla was saying that there's so much potentiality in my hand. Well, perhaps in a little packet of ether, I can store vast volumes of data, and it's that package. I'm not suggesting that that one package is being moved from here to there. No, the package is being transmitted just like the light from one part of the honeycomb to the next, so long as the signal is strong enough for it to receive that. So it's just my contention that actually what they're cleverly doing is they're not sending out waves in the way that we're drawing them on the piece of paper and this is how we see them.
Mm,
They're actually sending out that packet of ones and zeros into that piece of ether in a loud enough way that it can reach the next receiver and then pass it down the line in a different way. I mean, I just
mm,
distinguish this a little bit from the fiber wire, from
mhm,
because I can understand how well I can try and wrap my head around how little bits of light are being sent down that way and so cleverly done such that it can be received thousands of miles away and
mm,
interpreted as my voice and picture and so on. I can get that, but when it's just the air between me and my receiver two
mm,
miles away, then I'm starting to wonder, well, is it possible that it's actually the information, it's the ones and zeros that is being carried in the air, and it's the air or the ether that has the capacity to transmit that in the same way as I suppose we think about sound, particularly like in water, how that sound can be carried through, it's being sort of carried bit by bit, if you like,
mm,
passed down the chain. Here's a million ones and zeros, and it passes it down as long as the frequency or the volume of it is able to be carried in that
mm.
distance.
So, so kind of try to explain this to me again. So, when it kind of gets to your receiver, is it like, are you sending the whole packet in one go, in one fell swoop to your receiver, or how are you?
Yeah, no, I suppose not. I mean, it's going in order, I suppose, for the first second and to the last minute of the video. So, and it will take, I guess if you're in an environment, with a 4 or 5G thing nearby, you can download a video in minutes.
Mm,
But I accept that it's probably come in from minute one through to minute 120, in some kind of you know designated
mm,
order, so it's gone out as a chain of command. But just to simplify it and say, well, the first minute of it or the first second of it or whatever has to be the forerunner, and my device is sending that out. My router or my little TV, my little satellite dish on the roof, which is pointing at the local ground station, is sending that packet out bit by bit by bit and spitting it
mm,
out into the ether. Now, the question is that what we're all taught if we go into satellite engineering school is that you've got this noise, if you like, this frequency that's coming out, and that frequency is simply moving through uninterrupted, almost like a blank vacuum.
the
It's
vacuum,
just,
yeah.
yeah. and it's just going to go from here to the receiver, and there's nothing else that the environment is going to do to that. Whereas I'm suggesting that it's actually the environment that is carrying the signal, the
Hmm.
the waves and the signature.
Mhm.
So I guess that
Yeah,
would be my departure from the.
yeah, I kind of agree. Like if you take like the whole thing of kind of light traveling through a vacuum,
Hmm.
um, it's kind of it depends on how it depends on like kind of which framework you're looking at these things from, but kind of you can see like the transmission of a photon can be thought of kind of traveling through a photon field. So it's not necessarily it's the fact that these fields permeate all of space and all of time. So even the vacuum has has this kind of substrate. It's not like there's nothing like the vacuum doesn't have
Yes.
nothing in it. The vacuum
Yeah.
has these kind of
Yes.
overlaying structures on it.
Mm.
It just has to have no matter
Yeah. I
associated.
mean,
It doesn't mean that there's nothing there. It just means that there's like potential fields at these
yeah.
points.
Absolutely. I mean, when we talk about the vacuum, I know that we can create vacuum chambers on Earth, and the
Mm,
NASA one is probably the most famous. And I believe that in that environment, you've still got the background ether. You can
yes.
remove the gases,
Yeah.
but you've got the background stuff
Yeah.
that everything sits in, rides on in.
Mhm.
So I totally accept that, which is why I think you can send. I mean, you may not be able to get sound, but you can maybe send other things through that medium, and because the
Mm.
ether is still the
Well,
there's a
that
field
was
there.
kind of the weird thing with light was kind of what's it propagating through.
Mm,
Like all the other waves that we kind of experience have to have a medium.
yeah,
Um,
yeah,
it's like sound has to have air, or like
yeah,
when you tap a drum, it kind of vibrates the circuit. Like all of these things have to have a medium associated with it.
yeah,
And then kind of the physicists go on thinking about it and like, hang on, there's no medium. They're just kind of self, they're self interacting. But I think now more the modern view is that they are kind of propagating through this field, this quantum field. Um,
okay. Well, yeah. Well, I mean, it may end up one day in 10, 20, 30, 40 years time, people look back to calling it the ether, but I don't know, because
mm,
obviously, as I said, I think it gets in the way of special, as you said, and relativity. But it is my preferred thing. And then coming back to one of the things why I'm so kind of sure on this, as much as I can be, um, is the primer field experiments. They only work in a vacuum chamber with a gas, with a medium in it. Now,
mm,
now, what we were just saying is that even if I create a vacuum chamber, I've still got the background medium in it. I
yeah.
can't remove anything in this known world from
Mm,
the background field, quantum field. Um, so but in that he needs an ether, or he needs a to make it work, he needs like a gas in it, and he's tried it with different gases, argon, a bunch of others. They've done hundreds of experiments over the years. um so that's why I feel like, and one of my YouTube name is Trinity, which is a nickname I got given in the army a long time ago, but I brought it back out of the thing because in religion they go for the Trinity, that there's like a
mm,
Father, Son, and Holy Ghost Trinity.
mm,
But I think that in the electromagnetic thing, it can't just be the electricity and the magnetism. Is that there has to be this third
mm.
medium, which is the Trinity, from which you can then create life. You can then
Yeah.
begin to bring things about, but you need the three. Um,
Mm,
and and so I mean, this is really out there, Rob, but
mm,
but I even go so far as to suggest my thinking that, unscientific as it is that the medium is so not only so imperative and important to everything that goes on here, but it may be the very thing in which everything grows. So as I said earlier on about the light, and this is obviously not me, there's really good scientists saying this, but if the medium has the ability to be excited in such a way as to show up a light, if I point a light, if I point my
Mm.
torch and I'm exciting the medium and the medium brightens up, I wonder whether the medium, and as what Tesla was saying about it, has all this energy, all this potential
Mm.
in it. I wonder whether the medium doesn't actually carry the sort of DNA code, if you like, for everything that exists here.
Mm.
And that if a tree is growing, it actually grows in the medium. Let me try and think of an example of that. I don't actually have, I need to stop and think about that sometime. But I've been saying this for a little while and I haven't really had a scholarly discussion about this. But now that I am, I'm thinking, what good examples can I give of that? And perhaps in the lab, you've seen things grow in a petri dish that needed the medium for them
Mm.
to grow into,
Mm.
and it's almost like they grow because of the medium.
Mm.
They exist, they flourish, they take energy from the background medium.
Yeah, yeah, for sure. There's such a this is why I was so interested with talking to you, because like I think we're coming at it from two very different perspectives, but what you're saying has such the kind of crossover to kind of uh, the quite advanced kind of theoretical physics side of it. So the E and the B, the electric and magnetic field. Um, I think this is kind of what we discussed briefly, kind of in our email conversation. But the modern way of thinking about these things is to have them come from a potential field, what we call an A. You have
Mm-hmm.
an A field. So
Mm-hmm.
this can kind of be thought of as the background, and we do all of the calculations and all of kind of the predictions we make. It turns out these E and B things are too difficult to work with, so we end up going into this almost like higher A field. But this A field is um, non-physical, so it's not something that you can like touch, you can push. Like some may say that it's kind of like a mathematical abstraction
Mm-hmm.
above the E and B, but it's kind of there's been some the Aharonov-Bohm effect kind of says that this thing is actually there. Even how bizarrely that you can't like push it, you can't push
Yeah.
pull it, doesn't feel
Yeah.
forces, it's there.
Yeah. Yes.
And yet we have these kind of, and that's the background.
Yes.
That's the background. And then from this, you kind of get the electromagnetism, the physical
Right.
forces
Right.
coming from it. And we can't, oh, this is so exciting. We can't, we, we can't get the, we can't get like the modern understanding is this kind of thing that you can't like interact with. It's
Yes.
non-physical. You can't push or pull.
Yes. You
From
can't
that,
blow it. You can't do
no,
anything.
it's just kind of this background medium,
Yeah.
like the field,
Mm.
say. But then from the field, we get this, like we get the interaction things
Okay.
that we physically
Okay.
see. So maybe I don't know. Maybe that kind of goes into your kind of
It
Trinity
it does. I mean,
electromagnetic.
it's only obviously a coincidence that did you call it the A field and
The A field, yeah.
the ether have the same letter at the beginning.
Mm.
Just a coincidence, I'm sure. But that fits with this idea of, and I'm sort of have of the ether, is that it's not a thing that we can motivate. It's in everything. If you're pushing wind, you're pushing air, but you're not altering ether. You're not
Mm.
altering the kind of the background hum, the honeycomb that we're moving through. A fish doesn't know that it's in water, right?
Mm.
It's like background medium, and it
Mm.
just sees it as that. Now, I know obviously the difference is that you can motivate water, but yeah, no, that really is a fascinating uh, insight there. So you consider this A field as like it's sort of primary or prerequisite
Yes.
in order for stuff to happen down the line.
Yes, well, like the A field is the prerequisite for the E and the B
Mm,
to
mm,
occur, and
mm,
we do all of kind of the modern theoretic understanding of it requires this A thing to be, and it's basically we can't do any predictions, we can't make any sort of inferences about what's going to happen without this A. Um, and for the longest time, people thought it was kind of just a neat trick to make the maths easier. But I think it's kind of turned out that this thing is actually there, and as it in some sense, it's more. It's kind of what you mean by real, but it's more real than
mm.
the E and the B. It's
In the
kind of,
E.
as you said, it's kind of the prerequisite for these type of things to occur.
Yeah. Yeah, no, I mean that would be the order in which David Lapointe does his experiment, is that he puts these two oppositely charged magnetic poles suspended in this vacuum chamber, fills it with ether, and then or a gas. If the background ether is there already, but maybe the gas just gives it a coloration or something. But he does it in that order, and then fires the electricity into it, and then puts
Mm.
the electricity into it. Now he gets this accretion disk forming in between the two bowls, and it can take up a rotational movement and so on. It's just, for me, it's like, wow, am I looking at this tiny version of the Milky Way right there?
Mm.
Is that what I'm looking at? Because in mainstream they'll tell me that the Milky Way is like a flat galaxy. It's,
Mm.
when we look out, it's all really flat around us. Yes, there's stuff that obviously seems to be
Yeah.
up above us and then perhaps below us, but certainly the majority of the Milky Way is this frisbee
Mm.
of activity. Well, that's what I see with the primer field experiments, is this sort of frisbee forming, and they call it accretion, which is another word for creation. It's an anagram for
Mm.
creation, accretion. So I do consider that to be it. And when it comes to, like, so I mean, another way of thinking of the Trinity, of course, could be mother, father, child,
Mm.
um, and it doesn't quite fit with everything I was saying about the ether, electricity, and magnetism. So I'm not sure exactly how I explain that, and whether the child is now the fourth step, or if you start with, because you got to start in quantum. Hey, you got to start at zero and then inflate, or well, this is my understanding of it, is that you starting from a 0 point and then you're inflating up all the way to 9, and then you're kind of coming back around into zero again, like in a loop. And so, what would be the? It's been a few years since I looked at did this work, but it was like I could see almost like a progression up from zero to the one state, which would be like the ether base, and then you got this magnetism and electricity that come in perhaps 2 and 3, and then you got explosion of life, which would be 4.
Mm.
Anyway, I should go back on my notes on that and see if I can elucidate a little bit better. But just to say, in the sort of esoteric and spiritual way of looking at this, that there is this masculine and feminine interplay, which seems to be the precursor to the explosion of life or new life, or what
Mm.
the Catholic priest George Lemaitre called the Big Bang.
Yeah.
And I've started saying to people that I think the Big Bang is a kind of a joke, because the creation of new life is when your parents get together and have that
Mm.
moment, which is the bang. And in this microcosm, it may be that the male is the L, the electrical, offers
Mm.
the light through the sperm, and the female, she's the magnetic one, and has a magnetic. I'm going to say the zero. So I'm going
Mm.
to say the black hole,
Mm.
and the one, which is the light, is coming from the father, and the one smashes into the black hole and then is uh, brought to zero, brought into this state of the beginning of this creation loop that starts to
Mm.
separate cells and break the cells up into smaller and smaller or different frequencies. So that's how I see electricity and magnetism, is that they're possibly the masculine and feminine archetypes coming
Mm.
together and creating the next step.
I, I I really like that kind of that train of thought. Like there's a great book I read years ago that was kind of fundamental to this. It's kind of it's Maps of Meaning by Jordan Peterson. It's kind of his first. It's like before he got famous or anything. It's the kind of his academic
Okay.
work looking at kind of these archetypal stories.
Yeah.
And it's the same point, like kind of the masculine and the feminine, the yin, the yang. It's kind of, and he looks through the kind of commonalities in all of these ancient religions and kind of sees these kind of archetypes
Hmm.
playing out in
Hmm.
history.
Okay.
And I think there's something very fundamental to that. There's always like kind of this like feminine and this masculine force. And I think um, I can't remember. I think he has a lot to say about Christianity in it, but I can't quite. He does say something about the sun being kind of the thing that kind of rounds off all of this thing. But it's been years since I've read it. But
Okay.
it was definitely a very interesting book that kind of links to.
Yeah. Do you I mean, this may not resonate really, but so it feels to me like there's a lot of sun worship in the world, like in
Mm,
Christianity, Jesus is the son of
mm,
God and is often depicted with a sort of halo or sun behind
yeah.
his head. And ancient cultures sort of seem to be the sort of sun and moon worship,
Mhm.
and heliocentrism could
Mm,
be considered to be a form of sun worship,
mm,
because we acknowledge that without the sun we would not be here.
mm,
We needed the sun first, and then billions
mhm,
of years of stuff, and then Earth is habitable. And and so and actually, and then when the sun goes out, or when it swallows up or goes supernova or whatever it is that it's meant to do in billions of years time, then of course the Earth goes away.
mm,
And so we are completely sort of sun. For me it feels like that's how our science is today, is that that is actually hiding a form of sun worship.
mm. It's a weird one because obviously um, the special relativity, Einstein's first great insight, said that there's no special reference frame.
Mm.
There's no universe reference frame that you can say. Like how we normally do kind of physics is like, okay, here's the room
Yeah.
or here's the lab. The lab is the reference frame.
Yeah.
And then everything that goes about in it is kind of just
Within.
moving about.
Yeah.
Whereas what Einstein said is there's no preferred reference
Mm.
frame.
Yeah.
So you are the center of your own observable universe.
That's why people say to me, there's no up and down.
It's all
Yes,
relative
yeah, yeah. So like,
to your frame of reference.
yeah, you can't say that one frame of reference is more important
Mm.
than the other. They're like,
Yeah.
like I mean, technically, I see a completely different observable universe to what you see,
Mm,
and
mm,
there's no correct kind of
yeah,
way of looking at it.
Yeah.
There's no preferred reference frame.
Yeah.
So like you could say that the heliocentric model is just basically allows us to do easier calculations and kind of from my understanding it gets rid of like the problems of epicycles and stuff, but it doesn't mean that
Right.
like that shouldn't be a preferred reference frame,
Mm.
like theoretically, to any other. Like all the laws of physics are the same in every single other reference frame. There's no preferred one
Right.
to pick,
Right.
but you just pick the one that makes the calculations easier. So a lot of the headaches and a lot of the kind of the struggles of solving problems as a kind of an undergrad physicist was picking the right reference frame,
Right.
because as soon as you did it, the problem became easy.
Right.
But like if
Yeah.
you like if you didn't, then you'd have to do pages and pages and pages of calculations, and then your friend would come over and have like 2 lines of working, We're like, oh, how have you done that? I was like, oh, I've just picked this frame. I was like, oh, brilliant. But like, again, like we'll both get the same answer.
Yeah,
But one will take pages of working and one
right.
will take a couple of lines of working, but like it still works out the same. So
Yeah.
you could do all the calculations doing like epicycle stuff.
Hmm.
But kind of for convenience, we pick the sun as the center and we kind of
Hmm.
use Newtonian and Kepler's laws to get stuff that we predict.
Okay.
But it would be completely equivalent to do it another way.
Yeah.
Um, but again, it will just be more calculations.
Do you know that just now you mentioned Kepler, one of the little tidbits I know about Kepler was that when he was estimating the distance to the sun, it was 27 million miles. You get taught that?
I, to be honest, I didn't take a single astronomy module,
Oh, okay. Because
so
okay,
I'm in no position to kind of
okay. No, it's
argue
just
anything.
well, because the thing is that when we move the distance of the sun, then we obviously move the actual size of the sun because the apparent size is the same. But if I
Mm,
move it further away by 2 or 3 times the distance, then of course it must have been 2 or 3 times bigger all along in order to fit the model that I see or what my observation is. So, yeah, I used to say that to people in the street because I'd come across 13 different changes to the distance to the sun over the last
mm,
100 years by mainstream science. And Kepler's one has always stuck in my mind, the 27 million. But it was at one point, it was 3 million. And the
mm,
furthest that they ever predicted it was 103 million. And now they've
mm.
settled about 93, 94 million, something like that. Um, 8.5 light minutes or something. That's how they say.
Yeah, yeah.
I confess I'll never be able to fully understand how it's just a ray or it's a particular beam that's coming for 90 million miles through the blackness, coldness of space, in which there are so few particles that no heat can be transferred between one and another, which is why we can't measure how hot
Mm,
it is in the thermosphere. And then when it hits our atmosphere, magically it returns to a single ball of what seems to be very hot plasma or something. I'll never and I've had it explained to me by scientists in the street, but it's just so I'm like, okay, that's the explanation that we've been told, but I can't test that, and I have to just
mm.
either accept the explanation or say I think it might be something else.
Yeah, one of the reasons why I didn't particularly love astronomy is there's a lot of sitting and waiting for stuff to happen. Like
Mm,
the only medium that you can use to measure stuff is light, and now maybe gravity. But like light is the only thing that, and you can't set up experiments. So there's a lot of, oh, okay, we've thought about it, and this should happen, but we
yeah,
don't know when it's going to happen, and we don't know where it's going to happen. So we're just going to go and keep collecting data on the night
yeah,
skies until it
yeah,
does occur, and then it will confirm or deny what we just thought. But it just seems that there's a lot of kind of, whereas in basically all the other disciplines, you can go and like go to run to the lab and kind of set things up within a day and kind of measure it. There's a kind of, astronomy is unique in the fact that and
right,
they squeeze so much information out of the light that comes in. They've got like some like mind-blowing like observations that they can do just from like a little particle of light coming in. They can tell so
right,
much about
right.
what's
I
happening.
know, I know they can. Well, I mean, I used to be a believer in all of this stuff from Hubble and beyond,
Mm,
and so when they started saying we can see exoplanets going around suns
mm,
75 light years away, we can see that because of a certain blip in the light
mm,
so we're using receiving data, and we're starting to, with very clever minds, because universities are full of clever minds who are put to work that out. We've got this anomaly here, we've got this thing, and tell us what
mm,
it is, please. And so they've come up with some really fantastical theories that
mm.
I used to hoover up for
Mm.
my evening entertainment
Well,
because I found
that
that.
that's kind of like they used gravity as well. So they kind of looking at Mercury, kind of like the kind of traveling of Mercury. I can't remember when, probably 17, 1800s, but they saw this kind of anomalous kind of like twirling or something, and it couldn't have just been the sun that's causing that motion. And
Mm,
then they predicted that there might have been another planet there, Venus. It turns out, and then they do the calculations, say, oh, we might be able to see it this point in time on this latitude looking at in this direction,
Yeah.
and then it turns out that they can see that. So it's
Yeah.
just kind of amazing
Yes.
how this stuff kind of plays out.
Well, I think we live inside of an incredible, almost like the the best Swiss watch that has ever been made. I think that is
Mm,
it's like a timepiece that, and you know, you can, like Halley's Comet and these other things, you can
mm,
predict with incredible accuracy over decades and even
mm,
longer things that are going to happen, which is why I believe the Vatican is a big spender on mirrors, on
mm,
sky watches, because you know, I think that for me anyway, the movement of the stuff in the sky is a timepiece. But I also think that I accept relativity, but the relativity that I prefer, which is sort of, you know, along the lines of Einsteinian, but it's a way of saying, instead of instead of me instead of, you know, how in relativity, in very simple junior school terms, which is when I learned about relativity, where I stand on the top of the globe, you know, whenever in relative terms, I happen to be the observer and
mm,
I'm looking down from atop on the globe.
mm,
Well, I think the that that I'm going to say dome, but the vault of the heavens
mhm,
actually has a relativistic alignment on every observer. So when you and I observe the moon, for example, on a moonlit night,
mm,
we could be standing 10 miles apart. And it's a moonlit night. There's a bank of clouds set between your house and my house, 10 miles away.
mm,
When you stand outside your back door and you look up at the moon on a full moon night, you'll notice that there is a halo of light just above where you're observing the moon.
mm,
And then as you look away from that halo, it starts to dissipate the light. It gets weaker and weaker. And then 10 miles down the road where I am, it looks apparently dark. The clouds will
mm,
look dark. However, where I'm standing, 10 miles away, I'm having the same effect. I've got the spotlight almost of a
mm,
luminosity in the cloud bank above me. And then as I look back towards where you are, I notice that it seems to be getting darker. How can you be reporting this super bright
mm,
effect in the cloud above you? And I don't have a model. Um, I have some ideas, but I don't have a model necessarily that explains that. But it does make me consider the possibility that relativity is real. It's just that it's inverted in that it's not that it's putting you necessarily physically on the top of the physical Earth, but that the dome of perspective around you is centering itself on you as though you are at the center. And it's not to say that, you know, if you're standing on the equator, you can barely see, or you may not be able to see the North Pole star.
mm,
The closer you get to the North Pole star, then the more it creeps up
mhm,
into your towards above your head. And the same is true with the sun. As you move towards the equator, then you start to find it gets to center over you. And then as you go south of the equator, it starts to drop this
mhm,
way of you. Yes, absolutely. But again, if you stand on the beach at any one of these locations on Earth, the sun will bring its at sunset will bring its light right to your feet. And
mm,
that be true for everybody in the same way as that be true for everybody standing outside on a cloudy moonlit night will
mm,
say, I'm getting this same fog light, you know, street light in the fog, just apparently centered on me. And one of, you know, years ago, I was sort of really toying about this and watching, I was traveling on a train in England across the sun, or sorry, or the moon, I think the sun. And it was in the clouds. And I was just watching, and the train was going at full tilt. And I was just watching how it was just realigning itself all the time, sort of putting itself in
mm,
my line of sight. Obviously, it's dropping, it's setting, it's going away, it's doing
mm,
whatever it's doing. But at the same time as me moving, it just seems to be realigning itself. I'm not having to look back at it like this. Now, someone might say that that's to do with the 90 million miles it's so far away.
mm,
It appears as though it's just doing that. It's not
mm,
really that. But But I thought I would just throw that in at you, Rob, because well, because I think that there is a relativistic experience happening here.
Mm.
Um, it is, it is an individual, it is an individual avatar's reception of a particular signal, and depending on where they are, they will receive that signal in their own way, but centered on you, the individual. Not, I'm losing my way a little bit on this, but that's really just my thoughts on relativity, or what it's worth.
Yeah, yeah. I can't. I don't really know how to argue about kind of the moon and your train experience, and I'm not really the person to ask, so I don't really have any kind of experience in this domain.
But you can observe the moon. You can
Yeah,
observe this
yeah,
this
yeah.
thing of asking a friend who seems to be in the distance in the dark, according to your own observation. They
Mm,
will seem to be down in the village adjacent yours or whatever. They
mm,
will seem to be in a very low light part of
mm,
the cloud bank, but their experience will be no, it's very bright for me right here, even though it seems dark from your perspective.
mm,
And this is and so when you make this observation and you try and put that into either the heliocentric model, which says that there is a single reflector, which is sort of creating the super white light that some scientists claim that is, it's emitting a cold light that and I've done this with a laser experiment where you go in the shade of the moon and it seems warmer than it measures
mm,
warmer than in the direct moonlight itself. But notwithstanding, we if we test this in a lab and we say we've got one super bright football stadium light here, and we've got a 100-meter sheet or a 50-meter sheet of canvas or something that we're illuminating with it, then people on the other side of that sheet will see the whole sheet being, they should see essentially the whole sheet being illuminated, but
mm,
we don't, and we see this very odd experience that you cannot really replicate, I don't think,
mm,
in a lab setting, because where two observers can appear to have a very different light experience, not that there is one sort of blanket of illumination
mm,
across the 10 miles, just the 10 miles that I'm talking about. But of course, if you've flown at night, or you can have hundreds, thousands of square miles of cloud layer with the moon above it, and then every person underneath it will be all reporting their own particular hotspot,
mm,
but not a blanket of of illumination across as far as the eye can see.
mm,
So you may not have you don't need to have an answer on that. It's just an observation and it doesn't work with a flat Earth model, by the way, in which there is um a single source either, a single
mm,
point. Um, uh, you know, my preferred answer, well, my preferred theory on that, if I can share it with you, is that what we see as the sun and the moon are a secondary or an effect of a wave that washes over us. And depending on where you happen to be standing, because we can take this experiment onto the beach, you and I and five friends could be standing at different places off the shore in the water. One is 10 meters in front of the other, and another is 10 meters in front of that. And you've got a few to the left and the right of you as you walk into the beach. And each person will receive the wave. The person who's deeper in the wave, in the beach, in the water, will receive that rising wave first, and that'll be their morning. And it'll rise over them, and it'll peak at above their head. And as it's peaking above their head, it's starting to rise for the next person 10 meters behind them.
mm,
And if they're left and right, they will have about the same time that the wave will peak over their heads, but they would have a different, they'd be looking at a slightly different point on that wave, but their decoder would be detecting that zenith point as what we
mm,
call the sun, or in the case of the moon, and it would be doing that sort of magnifying glass effect of concentrating that point such that my eyes detect it as a single, blob of plasma or whatever.
There's maybe coming from like kind of a point of ignorance of the theory of just kind of like why, like as you said, I think the standard convention would be as to why kind of each individual observer sees the different brightness as to where they are, as the moon's just so far away. It's kind of like it's a not a parallax effect, but it's something to do with the fact that it is that far away. Kind of what is your like kind of problem with that kind of description of the moon, of kind of these celestial objects being that distance away?
Okay, well, I mean, I used to believe in the moon landing, so I don't trust NASA. Um, and I like to tell people that NASA was started by a guy called Jack Parsons. And Jack Parsons, JPL, Jack Parsons Laboratory, Jack Parsons was best friends with Walt Disney. And Walt Disney goes on to create this, you know, children's sort of stories about going to space and all the sorts of things that we can do, with Donald Duck and all of that. There was a trio of good friends, and the third of that trio was a guy called L. Ron Hubbard, who starts Scientology.
I do know.
So, so, so it's an interesting mix. And I learned along the way that they were students of a guy called Anton LaVey. The three of them were students at the same time of Anton LaVey, who was the leader of a group known as the Church of Satan. So, and that, I mean, that's all tittle tattle. That's maybe just, sort of irrelevant and so on. But in terms of the physical, and then of course the guy who does the Apollo programs, rockets program, is Werner von Braun.
Yes.
Now Werner von Braun,
I know the story.
yeah, so he's the paperclip guy, and he's the guy who writes the book about Elon.
Yes,
He takes mankind to Mars. Elon
yeah.
takes mankind to Mars in 1950. I mean, that's again one of those crazy old coincidences. Oh, wow. This guy who's so influential, and then he puts Psalms 19:1 on his tombstone, which is the bit about there being a roof and a firmament and so on, and from the Bible. That's the only thing he puts on his tombstone, which for an atheist, which is what I was, if I'd come across him with a Bible verse on his thing, I'd be like, hey man, you're selling out. What are you doing putting Bible verses on your thing? So and then because as a kid I read the Bible quite extensively. I had quite a lot of Bible study, and I used to tease the preacher about it being, the Bible talking about an earth that is out of touch with reality, because I was believing the science about heliocentrism, and the Bible has a geocentric, stationary, not moving place with small lights called sun and moon for days and nights and stars and so on. And so all of that, we can wrap up shortly.
Can I just interject? Like, I think my kind of opinion of these stories is they're kind of half empirical, half phenomenological, as in like half empirical, half psychological, as in there's true things to say about the real world and true things to say about the psychological world that we perceive like as conscious beings. So I think there's kind of an amalgamation of both of them. So I think there's still truth in these like ancient religious texts and these creation stories, but it's kind of as kind of science evolves, we can kind of get a better empirical understanding of it. But just to throw the kind of the psychological underpinnings of these stories and what they can say about human nature and like the way that we should like act and be and like what's true for conscious beings. I think that it's another powerful way of understanding what is like true, but it depends on what it's like. It always comes back to like, what do you mean by true? But I think it's still definitely important to kind of consider these.
Yeah. Well, I mean, I'm not I'm not like someone who needs the Bible in my life arsenal, but I you know, I think that there are some interesting and important messages in that. Whether or not the creation story as written in the Bible is correct or not um, is not my sort of landing point or my touchdown point. It's more just these are some of the things that when you put them all together, you're willing to question stuff. Like, for example, when it comes to the moon itself, um, obviously, you know, the moon landings, lots of skepticism about all of that. I watched the footage on the funny thing happens on the way to the moon of how nervous the guys look. Like these are the biggest heroes of mankind, and they look nervous and shifty and not clear and not like full of wow, you know, wow, what an amazing thing that we've done. More guilty. And you know, when Buzz Aldrin says to a young girl in 2015, you know, she says, why haven't you been back in 50 years? He says, that's not an 8-year-old question. That's my question. He says, the truth is we never went. Now everyone will say that he was drunk on the day, and that's you know, you don't want to take that too seriously. Same with the 2 cosmonauts who say we never went to Russian cosmonauts who say we never went. You know, you don't want to take them too seriously. But so, and then, you know, the sort of impossible elements of the moon landing that you know, originally I used to sort of be willing to accept the National Geographic story of what the conspiracy theory of the waving flags and the shadows and things like that on the moon, but just the, you know, just the kind of the practical stuff of, okay, so this lunar lander, you've only got, you know, 40 seconds of footage of Neil Armstrong barely holding the thing up until for 30 or 40 seconds, and then having to eject out of a a a bare chassis that has none of the body kit on it, nothing at all. It's just a chassis with some little rockets, and he can't steer that thing on Earth. And I used to accept the story that because of the 1/6 gravity up on the moon, it'll be no problem. They'll just get there and they'll do it. It'll work. Don't ask too many questions. Same with the spacesuit. You know, you look at the spacesuit of the 1960s, and they look nothing like today's spacesuits. You know, there's zips. It looks like gumboots. You know, motorcycle helmets that have been mildly adapted and so on. It's like, you know, and then they never put them in a vacuum chamber, these spacesuits, ever, with a man in it. You know, so you start to question the validity of that. So that's my preamble. What I will say is that when it comes to the physical moon itself, if I can zoom in with a regular commercial, I mean, a publicly available camera, and fill my viewfinder with a crater said to be 50 miles wide, is it possible that it's a lot closer? Because something that's 50 miles wide and 250,000 miles away in reality would never fill my viewfinder. Then we think about the craters that we see on the moon, and they're perfectly perpendicular, or there's no glancing blows, and yet the moon has always had the same face facing the Earth. And so therefore, how do rocks come in and hit it perpendicular if they're having to come in from the side? Because that would be the only way that things would be able to strike the surface of the moon. So are they really indentations from rocks?
From my understanding, that's the moon was spinning at some point, but because of kind of conservation of angular momentum and kind of how everything's in the globe model is kind of spinning, it kind of the rotation kind of slows as you go. So, you know, a couple of million years later, it fixes onto a single kind of face of what we see the moon. But at some point in time, it did have.
All right, I see what you're saying. So it could have,
which is
in
how
theory,
the places could come
that.
down. But again, this is I struggle to argue the kind of the astrophysics side because I really don't have any
that's probably the
experience.
best answer that anyone's ever given me as to how there could be that. I've never heard that said, but I accept that that's a, you know, that would give you a possible scenario. But it does also mean, but because there's no glancing blows whatsoever to be observed, it is an interesting thing that they're always going to come in at exactly perpendicular, because trying to hit a snooker ball exactly perpendicular every time is really difficult, and that you don't skid off the side. You know, you'd think that would be the case, but one of the things I observe about the moon that you may find interesting is that if it's, say, a half moon, and you're looking at it during the daytime, then the half moon that's in the shadow is exactly the same color as the sky. So it will be blue during the day, light blue or darker blue, depending on when you're seeing it and so on. And so NASA, apparently an article came out a few years ago saying that scientists have now realized that the moon is in Earth's atmosphere, which is why it picks up this blue color. But again, it's like, I don't know. You know, there's a friend of mine over in Canada who inadvertently was filming the moon, and inadvertently, only when he got back home, I think that he realized that he'd filmed a star through the shaded portion of the moon, through the part that's meant to be in shadow. But he was able to see a star through that. And that makes no sense with this idea of it being a rock or solid matter. And according to the mainstream science, and you won't know this obviously if it's not your field of expertise, but from the old moon to the new moon, there's a window that's about 20 hours in duration, during which the moon has never been observed. Never by science has it been recorded in this window between old moon and the new moon's first emergence and first observation of it. Now, if it's a rock, as we're told, then we should silhouette. It should be silhouette by the sun, because in our heliocentric model, and even in the flat Earth model, that the sun is traveling a little bit faster than the moon, or every 29 days, the moon is essentially going in front of the sun, such that we can't see any crescent or any reflection. That's the story. But if it was the case that it was going in front of the sun, even if it was at 5 degrees below or above, whatever they say it is, you should be able to spot that rock, particularly if you can spot an exoplanet 15 light years away. You should be able to see at 240,000 miles. You should be able to see the silhouetting of that. So there's a lot of things that we don't ask, or we're not taught to ask, about the way that the moon is. I said earlier on about people discovering that it seems to be a cold light rather than a moonlight, a warm light. It seems to have a rotting effect on plants and meat, a cooling effect on fire, which is the opposite of the sun. The sun is a healing light, and apparently it heats up a fire. Fires will grow hotter in the sunlight. And one of the other observations I wanted to finish off with, Rob, is that about in 2016, by the time I'd sort of gotten over my shock of, wow, the Earth is not, we can't prove the Earth to be spinning. And water is always level when it's at rest, but apparently a ship is going over the horizon. Was that actually I noticed that the moon is turning like this. That is actually turning like this. And the best way to see it is like in the UK, that I get a crescent moon. And if you see it in the afternoon and then can watch it for 6 to 7, 8 hours into the night, you will see it do this as it goes through the sky. The crescent will go from the side on, like the C, or backwards C for you maybe, and it'll roll like this, that you're actually underneath it. Now, if you had to take a flight to New York and carry on watching that same moon, it would carry on doing that while it traveled over America. That's that observation. I'm not satisfied that observation is explained by me happening to be on a rotating ball. It's tidally locked to me, this moon, and it's because I'm rotating somehow, or it's moving across my sky. Because I say to people, like, if I had to take this box here, this is not my office, I'm in someone else's office. If I had to take this packet of this Dunhill packet here like this and move it across your sky like that, you're always going to be able to detect that I've held it in the upright position. But if I started to rotate it like this, then yes, that's what you would see. You would see, oh, look, he's moving it, he's turning it. But if I took this from one side of a football stadium to another, you're still going to be able to tell me that I've got it in this orientation, not that I've rolled it like this. Well, the moon is rolling like this, Rob, in a clockwise fashion across my sky. And that's my observation, honestly, on observation for more than 5 years. And then when I went to South Africa in 2021, still watching the moon very closely, and I'm like, oh, hang on a minute, it's rolling anti-clockwise now. I'm in South Africa.
Mm.
Now I'm not convinced there's a flat Earth model or a heliocentric example that I could look to say, well, this is how you might replicate this. Other than to say that if I was to take, like, that bat light that the Batman used to shine, if you ever watched Batman as a
Yeah.
kid. Well, if I had to take that bat light and have it turn, because we're in a torus and we're in a rotating torus system, and whatever the moon and the sun are, they're associated to that. They might be the mouth and the butt of the torus, but whatever. If we're in a torus system and it's turning like they say, like the ether is turning at 15 degrees an hour. If it's turning like this at 15 degrees an hour, and if I'm over in Australia, I get to see the early part of the turn. And then in Europe, I get to see the middle part of the turn. And in the Americas and over into Hawaii, perhaps I see the later part of that turn. And if you Google crescent moons from around the world, you'll notice that people have got them photographed in different ways depending on where they happen to be. And that rotation, which was clockwise in the north, happens to be counterclockwise in the south. So if I took the backlight and shone it on a sheet, and then you stood on the one left side of the sheet and I stood on the right side of the sheet, I would observe a clockwise rotation whilst you would observe a counterclockwise rotation through the sheet of the same secondary reflective surface. That's honestly, the only model or way that I can replicate that observation. So that's why I have a lot of questions about the distance to the moon. As I said, if they've moved the sun's distance 13 times in a century, they've moved the moon's distance 13 times because they're all related, and it's the 400 times smaller.
It's easy to find relative distance. It's hard to find absolute distance.
Yeah. And so I've seen footage of the sun, for example, like with the moon. I was in Spain last year and I was watching this moon, but we were in a sort of valley, and I was watching the moon approach. I couldn't see the moon. I could just see the illumination starting to pop up, almost like in slow motion. Someone was driving a car up the hill, and it was just starting to kind of get brighter and brighter and brighter, and then pop, it would emerge just here, over on the crest of this mountain. And it was just a very local effect. I was taking photos of it and showing my family, look at this thing. It's right here for me. And there's some footage on YouTube of some pilots in the 747 or some commercial airliner where they're 40,000 feet or whatever. They're looking down on the sun inside of clouds, and it's right there. I mean, it's not like this is some secondary effect, or it's like you can see this glowing ball inside of the cloud, and they're laughing at each other and they're having a good old yuck about it because it's like such an incredible scene. Now, how do I explain that on a flat Earth model? I can't. How do I explain that with it being 90 million miles away and then shooting, parallel rays over a wall of 800,000 miles, and then it reaches this one point and coalesces into this hotspot that these folks are seeing? It's supernatural. That's when you start to get into this idea that maybe the individual observer is encoding something in the field that is what we are reading as that. And it gets esoteric. It gets to the idea that when you die, you take your sun with you, that your sun goes out, and your moon, you take that with you, and the world becomes a slightly darker place, as they say. And that we may, each of us, be the bearers of the light, that we may, when there are lots of people around a place. Okay, I'm getting way off in the weeds of esoteric there, but yeah, no, this world is fantastical, and exactly how it works, I really do not know. But I am scratching at this idea that we emanate the universe from that we see around us. We emanate it almost as a projection from ourselves. Your solar plexus, the place of the sun, may be the point out of which you're decoding this light that's out there. But I feel like that's probably enough for one session.
Yeah, no, I would love to, if we do this another time, I would love to discuss kind of the role that consciousness plays and kind of how we like how your kind of the esoteric theory kind
mm,
of plays in with like kind of the science and philosophy.
yeah, yeah. Because it's a genuine like wanting, and I know people say to me, "Oh, do you think scientists are lying?" No, I do not think scientists are lying. They're doing their
Mm,
damn best to try and make sense of the world. We all want to make sense of the world. I got to my mid-40s and thought I'm never going to be able to make sense of the world. I'll just keep watching the Discovery Channel and watch how scientists are trying to unfurl this. And I was looking forward to them finding life on Mars or on the moon. So I was genuinely wanting to understand that, but I think we are an expression of some higher consciousness, and
mm,
the world that we live in may be more matrix-like than we could possibly imagine. Maybe more, it comes from within you, and we can make the world whatever we want it to be. So if I convince people, like they did in apartheid, that one group of people are different to another, then people will live that way. And the same
mm,
is true with the heliocentric, or even the flat Earth model, because the flat Earth model is riddled with flaws and things that we don't know how they work. Um, and it may be none of these things is true, particularly true. It may be that our experience of the world is often predicated on the program that we're running. And that
mm,
program, if I've had your brain until 7, 10 years old, um, it could be to the victor the spoils, him
mm,
be the one that gets us to think who and what we really are. And the flat Earth versus globe Earth argument has been circling for 8 years now, or longer if but and I don't know that it's benefiting us, because we're not necessarily
mm,
using our prowess in the way that is most fruitful for us trying to really unpick the secrets of the world. But you'll know this from being a young scientist, that there's old scientists who, as I said it earlier on, who will cling to old models,
mm.
unwilling to consider alternative ways, because that was the model that they were welded to in their
But it
formative
always
years.
takes about a generation for these big ideas to come through.
Yeah,
The
yeah.
old timid professors die off, and then all the new scientists that kind of fall in love with these ideas come along.
Mm, mm,
So there is a definite kind of getting rid of the old guard in science that kind of stitch their views.
mm.
Um, but yeah, it
Awesome.
was fun talking. It's fun talking to you.
Awesome. Well, I really enjoyed that, Rob, and you're really well researched. But perhaps in a few weeks or something, we could schedule
Yeah, for
another
sure.
round. In the meantime, I will try and get. Well, no, I will get this. I will put this on my YouTube, if that's okay with you. Um, Really healthy, open discussion. No dogma, not too much of the dogma. Just some sharing of ideas, which I think is so much more constructive than us arguing over things that we may not be able to agree on, or even prove in some
Mm.
cases at this point in time. So I really appreciate your time.
Yeah.
Was
Thank you
there
for having me.
anything else you wanted to say just in
No,
before we end? All righty. Well,
but yeah, thank you very much.